Hello students, welcome to class. While you're getting logged in here, I would like you to open a tab with joinpd.com and enter the code ZBIFFX so we can get started on our pair deck. You may also want to open a tab for Desmo Scientific Calculator as well. ZBIFFX. Okay, so let's go ahead and get started. All right, to begin, I want you to take a look at each of these pictures and tell me which place you would prefer to swim. Okay, so you can either circle it, you can highlight it, you could write the number of the picture in the chat, up to you. All right, today we're going to be talking about functions, and we're going to do this by exploring freediving. Now, I don't know if any of you know what freediving is. Maybe you've done scuba diving, maybe you've gone swimming in the ocean, or you're a snorkeler, but we're going to be looking at the relationships between atmospheric pressure and depth. So, the objectives in this lesson are that you'll be able to create a graph using real-world data. You'll be able to interpret numeric values given an equation, and you'll be able to calculate depth and pressure given an equation. So what is free diving? Well, it's an aquatic sport where divers hold their breath and kick down to explore new depths. So some people, they may just go down to look at fish and corals. Sometimes marine biologists will go down and count fish or make notes about different organisms that they see down there. And then there's other people who train very seriously to set world records and see how deep they can dive. So we're going to look at the relationship between atmospheric pressure and depth in this lesson. Okay, so let's take a look at this table. As divers are going deeper, the atmospheric pressure increases, and we can see that in this table. One thing you'll notice is at 0 meters, there's already 1 bar of atmospheric pressure. Some people call the unit atmospheres, like 1 atmosphere or 2 atmosphere. We're going to call it bars. That's also used as well. So I want you to identify the pattern and then use the draw tool, use the text tool in here to fill out the rest of the table. Okay, great. So you guys all got that. You figured it out. It's going up by tens on the depth and ones by the atmospheric pressure. So I want you to note what is it about this relationship? What's increasing or decreasing? And I've given you a little starter here, but you can always add more to your answer or write a different pattern you see or something else you notice. Go ahead and write that using the text tool. Great. Okay. So now we're going to actually graph this data. So remember that each of these is an ordered pair. We have our x-axis, which is showing the depth, and our y-axis showing the pressure. So go ahead, use the draw tool to plot your points on the graph. Awesome. Great. So your graph should have looked something like this. And I want to take a look at this. So what do we notice about the graph? Is it linear? Does it change at a constant rate? Think about the definition of a function where we talked about, do the x's repeat? Does it pass the vertical line test? And just write something in there. Okay, great. I see that some of you said it is linear. Some of you noted that it is a positive linear relationship because as depth increases, pressure also increases. Awesome. Well done. Okay, so we can express this relationship between depth and pressure as a function, and we use this equation P equals 1 over 10d plus 1, where P represents atmospheric pressure in bars and D represents the depth in meters. So let's take a look at these two questions. Number 1, what does the number 1 over 10 represent in this equation? And number 2, what does the number 1 represent in this equation? So go ahead and take a moment to think about that and write your answer in the text box. Okay, great. So I see you guys thought this one through. When you think back to when we did linear equations, we talked about slope and y-intercept quite a lot. So some of you recognized that the 1 over 10 is the slope. It's the rate of change. And what is that saying? Well, it says that for every 10 meters that we dive, the atmospheric pressure increases by 1. Good. And then that plus 1, Some of you identified it as the y-intercept, which is correct. Some of you said, oh, this is the value when x equals 0. And in practical terms, what this is saying is when you're at sea level, you have you're at 1 bar of atmospheric pressure. Very good. Okay, so let's do a little calculation now. So Alexei Molchanov is the world champion free diver for the constant weight dive, which is just going down in your fins with like a weight belt. So he holds this record. He went down 130 meters on one breath. That's about 426 and a half feet. So think about how long he has to hold his breath to go down that deep. We're going to use this equation again, P equals 1/10 d plus 1, to determine how much atmospheric pressure was pushing on him when he was at that depth. So go ahead. We have, again, the depth was 130 meters, and you need to substitute that number somewhere in this equation to figure out how much pressure he experienced. Okay, so let's do this. Some of you have this exact thing. You did it perfectly. So we're solving for P, which is pressure. So we're going to take 1/10 times, we'll substitute 130 for the depth, plus 1. Now, 1/10 times 130, that's going to be 130 over 10. We add that 1. 130 over 10 simplifies to 13 plus 1. So the total pressure was 14 bars of atmosphere when he was down there. So that's quite a lot of pressure. And actually, in our next lesson, we're going to see how that affects lung capacity because, you know, this can be a dangerous sport if you're not aware of the mathematics going on behind it. So we'll look at that next time. For now, I'd like you to click on the link to complete the exit ticket, and it will take you to a Google form. Go ahead and complete that, and I will see you next time. Thanks for coming.